Let's determine the inductance of a coil that consists of N turns, is of length L, and whose cross-section has a radius of A. We know the magnetic field inside the coil is going to be much stronger than the magnetic field outside the coil. We can see that with how the iron filings line up with the magnetic field inside a coil but stay randomly oriented outside of a coil. So let's first use Ampere's circuit law to get the magnetic field intensity inside our coil. Our Amperian loop will go down the center of the coil, up and around, and we know the integral of H dot dl will equal the current enclosed by this Amperian loop. So down the inside of the coil, we'll get the magnetic field intensity inside the coil times our length L. The contributions to the integral of H dot dl from the other three sides of our Amperian loop will be negligible compared to H inside times L. The wire pierces the surface defined by the perimeter of our Amperian loop N times, and each time there's a current I coming up through the surface. So the current enclosed is N times I. So the magnetic field intensity is Ni over L inside the coil. So the magnetic flux density inside will be the absolute permeability of whatever material you might have inside your coil times H inside, which is Ni over L. So to find the magnetic flux, we multiply the B inside our coil by the cross-sectional area of the coil. So the B inside is mu Ni over L, and the cross-sectional area will be just pi times the radius squared, pi a squared. Our flux linkage will just be N times our magnetic flux. So we take our flux linkage and divide by the current to get our inductance. So here is the value of the inductance of our coil.